Hello, my name is Matthew, and I'm an application engineer here at Hawk Ridge Systems. In this video, we'll be going over a typical workflow to process data within Artec Studio 17, along with discussing some of the new tools released in this version. Per usual, Artec has introduced a ton of unique tools to clean up mesh bodies, process data, and extracting information from a mesh. We'll be using data from the Artec Leo that has been imported into Artec Studio. While this is one type of scanner from Artec, most of the workflow is the same for other scanners, and they can be viewed in our other Artec Studio introduction videos. We'll start by having our Leo project imported into Artec Studio. There are multiple ways we can offload Leo data. In this case, we'll be using the Wi-Fi method, by having the Leo and my computer on the same network. We can see our Leo appear in a list of connectable devices. Going into the Leo, we can see a list of all of our projects, and I'll import our most recent one. After a brief time of transferring the data, we'll see that our scan data appears in the list of objects. Just like in Studio 16, once a project is saved, it will continue autosaving after every command, ensuring that you do not lose any data due to a crash. Since we scanned with the HD data enabled for the Leo, and we chose to process the data after importing, we're given two sets of scan data, standard definition and the raw HD scan data. In our tools, we can run an HD reconstruction and choose the number of frames within the raw set of data to convert, as well as the level that we want our HD conversion to run at. When the process is done, a new set of scans with HD in their name will appear, one for each converted dataset. Looking closely, we can see that these HD scans have less noise data and deeper pockets of information, despite them having less frames within the scans than the standard one. Now that we have all of our HD scans, we can regroup our scans to clean up our workspace. By grouping and renaming scans, we can keep track over what data is our backup, parts of the object that has been scanned and what it relates to, and any other additional notes that we may need. Before we run any alignments with our scans, we can delete background data that isn't needed in the final mesh. Inside the eraser tool, we are given ways to select on our scan and erase parts of the scan. To remove tables and flat surfaces, the cutoff plane selection works well. We can select on a group of triangles and generate a cutting plane based off of that average. After adjusting the plane, clicking Erase will remove all of the highlighted red data. We can quickly switch over to another selection mode to remove floating bits of data that we originally missed. After cleaning up this scan, we can show the next one and erase data from it too. With all of the scans having their background info deleted, we can show all three of them and go into the Align tab and match points between the different scans to drive the alignments. Auto alignment is also an option, as well as many other alignment tools depending on the object you're scanning and if you're trying to troubleshoot a poor alignment. When aligning scan data, sometimes it's best to choose the scene display so that the scan only appears in a mono color, making it easy to select distinct features. In the list of scans, we can choose which scan can be registered to by double-clicking the scan name. Green scans can be rotated separately from the registered ones and will be the ones that move when we click Align. We want scans with plenty of data to align with as our registered one, which is why we have a scan with both sides of the guitar body to register our scans to. Most of the time with the alignments, choosing best fit, manually selecting 3 to 4 points to match the scans together will work and is the quickest alignment. The software will run an initial alignment, then a best fit based on the matching point selected. Clicking Apply will save our alignment once everything has been aligned together. Before we move on to the next step, let's talk about how each of these scans work. For the most part, scans are made up of a series of frames that are gathered during the scanning process. Similar to a panorama, these frames are aligned to one another based on similar geometry. During the scanning process, some frames may misalign and require troubleshooting to fix. For example, the bridge in this scan doesn't look the cleanest compared to the rest of the guitar. Running a rough serial registration, which will mimic rescanning the object and align each frame together sequentially, can correct misalignments like this. Sometimes we may need to go into the scan itself by double-clicking it. Here we can see each frame that makes a scan, and change the order based on the error values to go through the frames that are particularly out of place, or from the first to the last. Doing this isn't necessary for all scans, but there may be times where deleting specific troublesome frames can help fix a poor mesh. Rough serial and fine registration are used mainly for troubleshooting. When you're ready to continue processing our scans, we can run a global registration on all of them shown, and it will align each frame within those different scans together. We are given more options compared to the other registrations in global as well. For example, we can choose to run a registration separately on each scan, then collectively together. Which ratio of our scans will be keyframes to register between, how far we want to search for similar geometry, and if we want all of our scan data to be used during the registration process via the subsampling setting. We can also choose if we want to run a registration based on purely geometry or both geometry and color. Once your settings have been chosen, clicking apply will run the command, and when finished we see that our frames are well aligned together. With our scans aligned nicely, we can check the quality of the alignment either from the error values next to the scan or changing our scene settings. Under the orientation box is a drop-down menu to change how our scans look. Here we can change the color of our scans to show texture, monocolor, or even what our different frames and max error is. X-ray mode can be used to see if any parts of our scan are folding into itself, making it easy to identify non-manifold sections. For render mode, we can display our scans in a preview solid form, wireframe, or points to see how our point cloud looks. Utilizing the different options with the scene settings can greatly help with identifying troublesome areas and cleaning up your mesh. Now that our scans have had global registration run on it, we can continue on to the next step. Normally, if we were working with non-HD data or spacefighter, we'd have to run an outlier removal. This filters noise data within the scan, so it isn't included in the final mesh. HD reconstruction does this already, however, so for those HD Leo scans, we can move on to the fusion step, which is what actually creates our final mesh. Fusion will triangulate our point data to create a mesh from a combination of all of our scans. The three forms of fusion is fast, which only processes data within the scan and doesn't run any hole filling. Great to check the final quality of your mesh since it runs so quickly, but doesn't produce the sharpest image. Smooth, which will create a mesh and apply a smoothing on the entire mesh afterwards, is ideal for scanning human body parts. And last, the sharp is the most commonly used. All of the fusion processes have settings to establish the resolution of the mesh, which is the smallest feature that can be identified. In the smooth and sharp fusion, we can choose a hole filling option to make our mesh watertight so no holes will be in our final mesh, or to fill holes of specific sizes. If you plan to have a watertight mesh in the end, it's best to use the hole filling tools during the meshing process, since it accounts for outlier data that may not appear within the scan, but can be used to bridge gaps. Since we're using HD data, we can use the HD sensitivity, which we can set higher if we want things such as lettering to appear clearer. With our settings ready to go, we can click apply to begin the meshing generation process for all of our scans that are visible. With the fusion complete, a new object appears on our list with a box icon, indicating it's our processed mesh. Depending on the type of fusion process we ran, the name of the mesh will indicate it. We can see that the pegs of the guitar, which has a shiny material, did not pick up well and resulted in missing data. We can always add new scans to our data set and reprocess them into the mesh. In this case, I made 2 new scans of the turning pegs with talc spray on them to make it easier to scan. After aligning and rerunning a global registration, we ran a fusion process and the pegs came out much more clear in the mesh because we used better scan data. At this point, we can export the mesh as it is, but there are different post-processing tools we can run on the mesh to clean it up further before exporting. For example, the sound hole was partially filled since we chose the watertight for our fusion. We can try and add more data around this area, or fill it in and add the hole during the modeling process. Back inside the Eraser tab, we can choose our tools to highlight the generated mesh data and remove it. There are different ways to select this data, such as the 3D sphere or object selection to grab large portions of floating data. For smaller features that may be hard to select, the small object filter can be used inside of the Tools tab. This will remove all floating bits of data except for the largest cluster of the mesh body. If we expand the Properties tab and select on our mesh, we can see the total number of polygons. The larger this number, the bigger the file size is, so reducing the polygons can make working with the mesh easier in other programs. In the Post-Processing tab, we have tools to simplify the mesh, either using certain parameters or just a desired polygon count. In this case, we'll use the Fast Mesh Simplification to quickly reduce the polygon count from 3 million down to 2 million. Keep in mind that you can often reduce a mesh's polygon count by 70% and not notice a single difference in the mesh's quality. Since we deleted the sound hole, we can choose to go back and fill it in. This may make surface modeling easier or make for a nicer render. Fix Holes tab is handy to correct and fill any holes of the mesh. While there is the Fill Holes tool, or the ability to do it during the fusion process, the Fix Hole tab has additional functions that we can use. For example, we can choose to fill a hole with the shortest paths or a tangential fill using the smooth or flat options. We can also smooth the edges of our hole to remove spikes that may throw off the hole filling algorithm. The Bridges tab can also be handy to break larger holes into smaller ones. You can control the arcs of the bridge and how wide it will be. Bridges are handy if you have a sharp edge that you need to also hole fill properly without it creating a bubbling effect with the fusion process. Once all of the holes have been corrected, we can click Apply to save them to the mesh. Looking at the hole fill, there appears to be some differences between the bridge and the mesh edges that the hole fill created. Our Editor tab has some handy tools to correct these issues, like the smoothing brush. This tool will smooth out selected areas, blending the mesh and edges together to make features easier to apply textures onto and model from. Now that our mesh has been cleaned, we can export it via our File Export Mesh option, where we can choose it as an STL type, which is a neutral mesh body type to import into other softwares. At this point, we've created our mesh and it's been exported. We've gone through multiple steps, and you may find that you'll be using the same settings for multiple different projects. To make processing data easier, there is the Auto tab inside of Tools. Here we can click on checkboxes on processes we want to run on our scans, and they'll be run sequentially based on the settings we choose in the Manual tab. Or, if you aren't sure what settings to choose, the Autopilot tab will walk you through the entire processing steps and ask questions to help choose settings. It will first ask if you want to clean and align your scan data, then run a global registration, outlier removal, and fusion steps based on the questions asked in the earlier prompts. This is handy for new users who aren't sure what to choose yet for the manual settings when processing scan data. There's still more to show off, however, inside of Artec Studio. So far we've just created a mesh, but we can extract more information and add color to this mesh. Inside the Texture tab, we can project the color from our scan onto the mesh. After selecting the mesh we want to apply the color onto, and the scans we wish to pull the color from, we can choose additional settings, such as adjusting how the texture can be filling in missing areas, reducing the glare from the scanner, and what resolution we want the texture at. Texture Destination will package our color map up. Preview only shows the color on the mesh and isn't ready for export until we choose the export option in the texturization process. Additionally, the color is being projected from the scans, so choose scans that are aligned to the mesh itself. When the process is done, we'll see our mesh appear with the color on it and additional slides to adjust hue, saturation, and brightness. Keep in mind that the scanner is producing its own light source, so if you have a part that is very glossy, the texture from the scanner may change depending on the angle you're scanning at. To correct this, we'll talk about another process to gather color information. Introduced into Artec Studio 16 and improved in 17 is the ability to add photos from a camera to be used in the texturing process. Objects that may need richer color or glossy from reflection based on the different angles, like this guitar, can have their color corrected by importing in photos taken during the scanning process. This painting, as we can see, has washed out colors in glossy sections in the middle. Photos can be taken at different positions and imported into Artec Studio via the import options. They'll be broken up based on the focal length that was set when the photo was taken. We can also preview each photo that's imported to identify blurry or unneeded and delete them from our import list. To align the photos to our object, we'll first have to process the data until it's a mesh and it has color applied from the scanner. We can then show the mesh with color, the scans that made that mesh, that coordinate to the photos, and the imported photos. The photos align well when they match the position that the object was in when being scanned. Once the alignment finishes, we can see how each photo matches to the scan by double-clicking the photos in the 3D space or in our photos list. When everything looks well, we can go into the Texture tab and rerun the texturing process and select on the photos to project. With the photo texture, we can see that the color and sharpness has vastly improved on this painting, as well as having an even coloring throughout the entire mesh. Artec Studio 17 added several new tools related to the CAD alignment, measurements, and CAD generation. If you have a CAD file of an object you scanned, these can be imported and aligned to our mesh. Since the meshes keep their orientation during export, we can set up a datum alignment so specific faces of the CAD file drive our mesh's alignment. An initial alignment must be done first. After, we can click on the Align by Datums option, which appears in our Alignment tab, and select on specific faces we want to choose as our datums. It will show us an estimated deviation from the datum face, and we can even show a 3D color map of the alignment in the tool too. There are additional measurement tools available in the Measures tab. We can generate a more in-depth color map in the Distance tab that compares a mesh to a CAD or another mesh file. We can adjust the search distance and the tolerance to adjust our color map as well. If we want to measure between 2 points or 2 CAD objects, the linear distance tool can be used. If a geodesic measurement is needed that follows the curvature of the mesh, we can create one as well. This will take longer to process, however. The last tab is Sections and Volume, which is very handy to calculate volume and surface area or the perimeter of the mesh. We can generate a cutting plane based on the orientation to a world coordinate system or a constructed points. When we generate the section, the areas highlighted in red will be calculated for volume and surface area. We'll also see green spline lines that appear around the edge of our mesh. These can be exported as a DXF and imported into other softwares to be used as reference sketches. Going to the Construct tab, there has been several new ways to extract and have mesh data interact with CAD features. We also have new ways to select on our mesh to extract out CAD features using the flood selection. With this enabled, we can select on a part of the mesh, and the software will auto-select similar triangles to the original selection, as well as ways to adjust how sensitive the auto-selection is to curved features. This is very handy if you want to select on a small or a large area of data. With our data selected, we can choose the primitive CAD features we want to generate based off of the average of our triangles that are highlighted red. The different selection methods can be useful to grab specific areas separated from one another, or the flood selection doesn't properly choose. We can also remove some of our selected area by holding down the Alt key. Sometimes we have parts of our mesh that have lettering that can throw off our feature generation. To remove these, we can go back inside of the Editor tab and choose the Defeature tool. This will allow you to select on areas of the small features of the mesh and remove them and fill them in tangentially to the surrounding area. Now that we have 2 CAD features extracted, we can pre-align them together using the CAD constraints. Parts in the real world may not be 100% parallel or perpendicular to one another. Using constraints, however, we can extract out CAD models from our mesh and ensure that they are properly oriented. In this case, I'm making the bottom face of this cone to be parallel to the bottom plane. First, select on the CAD feature you want to move, the type of constraint you want to use, and then select on the CAD feature you want to constrain it to. Clicking Refit will build our CAD features with these constraints applied. You can have multiple constraints on a single CAD feature, and these can be added after exiting the tool by going back into the Construction tab or double-clicking the CAD feature in our object list. The fitting mode will adjust how the CAD feature is generated from our selected triangles. Exact will create a feature based on just the highlighted triangles. Robust will find the largest average of the triangles in the selection and generate the feature from that, handy for surfaces that might have bumpy patterns or slight wear. Expanding will look for similar triangles to the selected one and generate the CAD feature from them, which may be nice if you only have a small section that you can choose from. For freeform surfaces that can't be expressed through simple CAD models, we can use the Surface Extraction tool. We will still select on the triangles we want the surface to be generated from, but now we have settings based on control points, which can be used to generate the surface versus a fitting method. Padding will expand the generated surface beyond our selected triangles. Number of points is the control points that the surface will use to reference the mesh body, and order is the number of spline lines to generate the surface. As we increase points and order, our surface will become more accurate to the mesh, but increasing it too high may cause warping and not have a smooth surface body. In surfaces, we also have the new Auto Surface tool, which will generate a one-to-one CAD model of our mesh. Increasing the number of patches will increase the resolution of our surface patch, leading to a more accurate model, and T-Node allows for sharper edges to be generated easier. This is very handy if you want a quick CAD model of your skin to work off of in another program for hybrid modeling. The next tab in Construct is Create, which will let you create a CAD feature without extracting anything from the mesh. Some features may not have enough data to properly generate, so we can use this tool to create and align a CAD feature to our mesh to use in the future. The last tab is Edit, also new inside of Studio 17, which can be used to merge or cut CAD features from our mesh body. This is an incredible tool to make mesh files easier to print or clean up parts of the mesh for inspection. We can use the Split with Plane tool to cut a mesh based off of an extracted plane. This will generate 2 mesh files based on how the plane intersects with the mesh. We also have Boolean tools which will remove CAD features from the mesh. Here, we're using an extracted cylinder to remove the filled-in mesh information from a hole we didn't fully scan. Once the Boolean finishes, we have a proper hole versus the partially filled one made during the meshing process. Being able to use the merge, split, and subtract tools, we can drastically change our mesh file in areas that didn't properly mesh, but need exact geometry or add information that may be handy for inspection and printing. The last edit tool is Intersect, which generates a new body based on where two features intersect. We've talked about how the mesh will export in the orientation it's currently in, and now that we have some CAD features extracted, we can use some new orientation tools to align our mesh. We can use the rough positioning tool to quickly orientate our shown objects based on a couple of control points. If you want to make one side match a coordinate system, this is a quick and easy way to do this. If you have CAD features extracted, however, we can use the precise positioning to set up a datum-based alignment to the world coordinate system. Here, we can choose on different features that we've extracted to establish an origin, normal direction, and primary alignments. With two planes in the cylinder, we can properly align this block to an XYZ plane, with the center being on the cylinder's axis. With it aligned to a coordinate system, we can also go back into the Editor tab and run a transformation alignment to make minor adjustments to its orientation. We also have the ability in here to scale our mesh or mirror it across an axis. Artec Studio 17 not only improves existing tools, but greatly expands the CAD extraction and photo capabilities within Artec Studio. There are several ways to approach a project, but hopefully from this video you can see the standard workflow to go from a raw scan to a finished mesh. If you're interested in learning more about these tools, check out our other Artec Studio videos, as well looking into the user manual that has more in-depth information about each setting and their tools. For more videos on Artec scanners, printers, or engineering software, subscribe to our YouTube channel.